The James Webb Space Telescope is transforming our understanding of the universe with unprecedented insights, and this new level of clarity is what makes this remarkable instrument so thrilling. Positioned far from Earth, Webb continuously astonishes scientists with discoveries they never anticipated or can readily explain. Recently, it unveiled an astonishing discovery, dubbed the Sentinel, hinting at artificial lights originating from a distant world nearly 7 trillion miles away. This surprising observation has ignited a fresh wave of curiosity about the potential for extraterrestrial life. But has the James Webb Space Telescope truly found signs of life beyond Earth? Join us as we delve into this groundbreaking discovery and explore its implications for future space exploration and our understanding of life beyond our planet. In January 1992, two radio astronomers, Alexander Wolszczan and Dale Frail, made a discovery that reshaped humanity's view of the cosmos. Wolszczan was studying pulsars, fast-spinning stars known for their distinct emissions, when he detected an anomaly that didn't match typical pulsar activity. Curious, he investigated further and eventually identified two planets orbiting the pulsar. His colleague Frail confirmed the findings, and together they made an announcement that sent ripples through the scientific community. They had discovered the first confirmed planets orbiting a star outside our solar system. These exoplanets provided the first definitive proof that planetary systems existed beyond our own, fueling a surge of interest in finding and studying exoplanets. The search for exoplanets has rapidly progressed, driven by advanced tools like NASA's Kepler Space Telescope, launched in 2009. Specifically designed to detect exoplanets by observing small dips in starlight as planets pass in front of their stars, a technique known as the transit method, Kepler has revealed over 5,000 exoplanets. These findings have unveiled a stunning diversity of worlds, some resembling Earth in surprising ways. Each discovery provides answers about planetary formation, while raising deeper questions. What types of planets might support life? Could there be worlds capable of sustaining life in ways beyond our imagination? In response, a new generation of space telescopes has been developed, including the James Webb Space Telescope, the most powerful of its kind. Often seen as Hubble's successor, Webb has a 100-fold increase in power and an orbit 1.5 million kilometers from Earth near the second Lagrange point. This position keeps it free from interference from the Sun, Earth, and Moon, allowing it to operate at an ultra-cool temperature near -225 degrees Celsius. This cold environment is essential for Webb's primary observation technique, infrared imaging. Infrared light enables Webb to pierce through dense gas and dust clouds, revealing young stars and planets that are otherwise hidden in visible light. One of Webb's primary missions is to observe the early stages of planetary formation as gas and dust clouds collapse into stars, surrounded by swirling material that may eventually form planets. As Dr. Jane Rigby, a project scientist for Webb, explains, space telescopes provide sharper images, unaffected by Earth's atmosphere, especially in the infrared spectrum. Free from atmospheric interference, Webb can analyze young planets' structures and compositions with remarkable clarity. Equally groundbreaking is Webb's ability to perform spectroscopy, a method of analyzing light to determine chemical compositions. When starlight passes through an exoplanet's atmosphere, it undergoes subtle changes, leaving imprints of various elements and molecules. By splitting the starlight, Webb can detect these signatures, identifying components of the atmosphere, such as water vapor and methane, potential indicators of life. As Rigby notes, this marks our first opportunity to examine the atmospheres of exoplanets, particularly those similar to Earth, in such detail. Since its launch, Webb has begun to unravel the mysteries of distant worlds, observing planets like WASP-107b, a scorching exoplanet over 1,300 light-years away with an atmosphere of vaporized rock and floating quartz crystals. Webb has also studied GJ1214b, the sauna planet, with a mass 8 times that of Earth and a steamy atmosphere. Even more intriguing are the rogue, Jupiter-sized planets drifting through the Orion Nebula without any parent stars. Each planet challenges our understanding, expanding our knowledge while presenting new puzzles. Among the exoplanets ripe for Webb's exploration is Proxima Centauri b, our closest known exoplanet neighbor, discovered in 2016. Proxima b quickly captivated scientists due to its location in the Goldilocks zone of its star, Proxima Centauri. This habitable zone is the ideal distance from a star where conditions could allow liquid water on a planet's surface, a key ingredient for life. Proxima B's proximity to its star provides it with adequate warmth, sparking interest from astronomers eager to find a planet with Earth-like characteristics. With a mass about 1.7 times that of Earth, Proxima b may have the potential to retain an atmosphere which could protect its surface from space radiation and help maintain temperatures favorable for life. Although Proxima Centauri, a red dwarf, is much smaller and cooler than our Sun, Proxima b's close orbit could allow it to sustain Earth-like conditions. Scientists believe its temperatures may fall within a range that permits liquid water, a crucial factor for life. Over the years, Proxima b's potential habitability has fueled speculation about whether it might possess a thick, protective atmosphere, and perhaps bodies of water like oceans or lakes. Could life, either primitive or advanced, have developed there? These questions about Proxima b's landscape and potential for life have deepened with recent observations by the James Webb Space Telescope, offering new insights and further fueling excitement about the search for life beyond Earth. Recent studies reveal that the Webb telescope has achieved an unprecedented level of clarity in imaging Proxima b, capturing its atmospheric characteristics, surface temperature distributions, and more. This exceptional detail is providing scientists with fresh insights into Proxima b's potential habitability. The telescope's observations even cover the dark side of Proxima b, a region shrouded in permanent shadow due to tidal locking. This phenomenon keeps one side of the planet constantly facing its star, while the other side experiences perpetual night. Such tidal locking raises intriguing questions about temperature variances and potential atmospheric circulation, factors that may impact Proxima b's overall environment. Yet, what the James Webb Telescope detected on Proxima b's night side has left scientists both fascinated and puzzled. It observed unusual emissions of light originating from the perpetually dark region, emissions that did not correspond to known natural phenomena like volcanic activity or atmospheric auroras. These findings have led to speculation that the light patterns might be artificial, resembling the city lights visible on Earth's night side when seen from space. Although it may seem improbable, the idea of detecting artificial lighting from an exoplanet over 4 light-years away is made possible by the telescope's advanced infrared sensors, which can detect faint emissions of light and energy across vast distances. Remarkably, the observed patterns on Proxima b's night side displayed an unexpected regularity, forming grid-like configurations, an anomaly among known natural phenomena. If these grid-like patterns are indeed artificial, they could indicate the presence of city lights, marking one of the most groundbreaking revelations in the search for extraterrestrial life. Such a discovery would not only suggest the existence of intelligent life beyond Earth but would also imply that an advanced civilization resides relatively close, in cosmic terms, just beyond our solar system. At roughly 4.24 light-years away, this proximity would revolutionize our understanding of humanity's place in the cosmos, challenging the long-held belief that intelligent life, if it exists, is likely found at incomprehensible distances, or perhaps does not exist at all. Knowing that intelligent beings could live so close would reshape our scientific paradigms, philosophical perspectives, and collective cultural identity. Humanity would no longer be left contemplating the possibility of extraterrestrial life. Instead, we would face the reality of sharing our galactic neighborhood with another civilization. This revelation could prompt questions about the nature of this life, its level of advancement, and its history, culture, and technologies. Scientists might even wonder if this civilization is aware of our presence on Earth and, if so, how they perceive us and our efforts to reach out into the stars. These questions would spark further research, inspiring a new era of exploration driven by a desire to understand our cosmic neighbors. The ripple effects of such a discovery would extend beyond science, impacting philosophy, sociology, political science, and religion. It would challenge our long-standing assumptions about our uniqueness and our role in the grand narrative of life in the universe. The discovery would evoke both awe and vulnerability as we come to terms with the realization that we are not the sole intelligent beings in our corner of the cosmos. It would almost certainly ignite a global movement, unlike anything humanity has seen before, to explore, and if possible, make contact with this extraterrestrial civilization. For centuries, humanity has pondered whether we are alone in the cosmos, a mystery that has inspired both scientific endeavors and boundless fictional worlds. The tantalizing possibility of intelligent life so close to Earth would fuel an unstoppable push to bridge the cosmic distance, becoming humanity's greatest challenge and purpose, the dream of connecting with another civilization. Today, even with our advanced technology, humanity's ability to explore the far reaches of space remains limited. Our current technology would require decades, perhaps even centuries, to reach Proxima b, given that it lies approximately 4.24 light-years away, or nearly 40 trillion kilometers. Presently, Voyager 1, the fastest human-made object, would take over 70,000 years to reach Proxima Centauri at its current speed. Such a timeline makes the prospect of interstellar contact seem unfeasible. However, discovering artificial light on Proxima b could change everything, driving the urgency to bridge that distance and spurring unprecedented advancements in revolutionary technologies. Concepts once relegated to science fiction, like faster-than-light travel and communication technologies, might become essential in this new age of exploration. Ideas such as warp drives and wormholes, previously dismissed as speculative or unrealistic, might soon become serious subjects of research, attracting scientists, policymakers, private companies, and the public. With newfound purpose and funding, these theoretical technologies could move from the fringes to the mainstream of scientific inquiry, as humanity would no longer have the luxury of dismissing them as impossible. The chance to communicate with another civilization would make such advancements urgent, perhaps even inevitable. One concept, the warp drive, has long fascinated scientists and captured the imagination of science fiction enthusiasts. Popularized by franchises like Star Trek, a warp drive could enable faster-than-light travel by distorting space-time. The theory suggests that if a spacecraft could create a bubble around itself, contracting space in front of it while expanding it behind, the vessel could ride this wave of warped space, effectively achieving superluminal speeds without violating the laws of physics. This idea may seem like fantasy, but researchers like NASA's Harold White have explored its feasibility, concluding that it may not be entirely impossible. Although far from being realized, this theoretical framework offers a glimpse into a future where interstellar travel might become attainable. If we detected artificial light on Proxima b, warp drive research could no longer remain a mere thought experiment, it would become a crucial goal of scientific research. The potential benefits are enormous, a technology that could allow us to reach Proxima b in a fraction of the otherwise required time. Currently, even at the speed of light, the journey would take more than 4 years, but with a warp drive, this trip could be reduced from millennia to mere years, offering the first real hope of bridging the vast distances of space and making first contact a possibility within a human lifetime. Another technology that would likely gain unprecedented focus is the concept of wormholes. In theory, wormholes are shortcuts through spacetime that could connect distant points in the universe, enabling instantaneous travel. While wormholes have been a staple of science fiction, they also have roots in the physics of general relativity. Physicists Albert Einstein and Nathan Rosen first proposed these bridges in spacetime, later known as Einstein-Rosen bridges or wormholes. Currently, wormholes remain hypothetical, with no real-world examples or applications. However, if we confirmed the presence of an advanced civilization on Proxima b, it would change our research priorities, making wormhole studies imperative in the hope that this civilization might have already mastered this technology. Learning how they achieved it could guide humanity toward breakthroughs in our understanding of physics, ultimately allowing us to create stable, traversable wormholes. The discovery of artificial light on Proxima b could usher in a new era of space exploration centered around wormholes. If this technology could be harnessed, humanity might achieve near-instantaneous travel between Earth and Proxima b, turning interstellar travel into a tangible reality. For the first time, we would possess the ability to journey beyond our solar system, shifting humanity's place in the cosmos forever. Alongside the pursuit of faster-than-light travel, this discovery would intensify the demand for faster-than-light communication, given that Proxima b is over 4 light-years away. Communicating via traditional radio waves would entail an 8-year round-trip delay, 4 years for a message to reach Proxima b and 4 more for a response. Such a time lag would hinder any meaningful dialogue, especially if we sought to establish diplomatic or collaborative ties with a distant civilization. Quantum entanglement, a promising approach to overcoming this barrier, could hold the key. This phenomenon links 2 particles so that the state of one particle instantly affects the other, regardless of distance. Though controversial, some researchers believe quantum entanglement might enable faster-than-light communication. Should artificial light be discovered on Proxima b, physicists would face immense pressure to unlock the mysteries of quantum communication. The resulting research might lead to the development of a reliable communication network, capable of enabling instantaneous messaging across vast distances, revolutionizing our interactions with extraterrestrial civilizations and potentially facilitating seamless communication with future human colonies on other worlds. The discovery of artificial light on Proxima b could also have profound social and political implications, likely sparking an unprecedented level of international cooperation and innovation. Similar to the space race of the 20th century, the quest to reach Proxima b might initiate a new era of scientific rivalry while fostering collaboration across borders. The stakes in reaching Proxima b would be astronomical, with governments recognizing the magnitude of this endeavor and viewing it as an opportunity to place humanity on the universal stage. The potential to encounter another intelligent civilization could inspire a drive for global unity, as nations understand the importance of presenting a unified front when approaching this alien society. As institutions like CERN and the International Space Station have united the world's brightest minds to tackle complex scientific questions, a similar, if not greater, level of collaborative effort would be needed to communicate with Proxima's inhabitants. These alliances might manifest as multinational agencies and research partnerships dedicated to interstellar communication, each leveraging its members' strengths and resources to confront extraordinary challenges. This mission would also demand entirely new research institutions, particularly those focused on developing faster-than-light travel and communication technologies. Imagine facilities solely dedicated to breaking the light-speed barrier, allowing messages to traverse light-years in moments. Such institutions would become hubs of innovation, where scientists, engineers, and visionaries from around the globe would work to create methods of interstellar communication once limited to science fiction. This research could lead to advancements in physics, energy production, and propulsion, driving breakthroughs that would redefine humanity's reach in the cosmos. As governments and research bodies rally around the Proxima b mission, the private sector would likely experience a surge of involvement and investment. Inspired by trailblazers like SpaceX, private companies would seize the opportunity to contribute to this monumental effort. SpaceX's influence, particularly its success in making rockets reusable, demonstrates how private ventures can propel humanity toward ambitious goals. Companies focusing on space exploration, biotechnology, and advanced material sciences would experience immense growth as they contribute to humanity's quest to connect with another civilization. These private enterprises would compete to develop advanced technologies, from propulsion systems capable of interstellar travel to biotechnological innovations aimed at sustaining human life on foreign worlds. The push to reach Proxima b could transform the private sector into a powerhouse of space-focused industries, sparking new companies and markets around the challenges of interstellar exploration. This fusion of public and private sectors would be unprecedented. The commercial space industry might witness a renaissance, with corporations heavily investing in spacecraft and research systems to bridge the gap between our solar system and Proxima b. Just as the Internet spurred the creation of countless new businesses, the discovery of intelligent life could catalyze a new industry centered around space technologies, interstellar communications, and planetary sciences. The Proxima b mission might inspire private companies to pioneer breakthroughs in energy storage, radiation protection, and habitat construction, all essential for sustainable deep space travel. Biotechnology firms would also play a crucial role in the mission. The hostile conditions of deep space demand enhanced human resilience, and research into gene editing, bioengineering, and artificial life support mechanisms could become central to these efforts. Companies specializing in materials science might focus on creating durable, lightweight materials capable of withstanding the harsh conditions of space. Altogether, the quest for Proxima b could spark a renaissance in science and engineering, fostering collaboration between scientists and business leaders and transforming once futuristic technologies into feasible solutions. Beyond technological and scientific realms, the discovery of city lights on Proxima b would ignite profound philosophical and ethical debates. Humanity has long speculated about the existence of extraterrestrial life, but these speculations have remained theoretical. Concrete evidence of intelligent life would bring ethical questions surrounding contact with another civilization to the forefront. A key ethical dilemma would be whether we should even attempt to contact the civilization on Proxima b. While city lights might suggest technological sophistication, we would have no way of knowing whether this civilization is friendly or hostile. Could making contact put humanity at risk? This question has sparked debates among scientists, philosophers, and the public, highlighting both the potential for profound benefits and unprecedented risks. One major argument for caution draws from historical analogies. Encounters between technologically advanced civilizations and those less advanced often led to domination or even annihilation of the latter. The arrival of European settlers in the Americas, for example, had devastating effects on indigenous populations, whose societies and ways of life were forever altered or even destroyed. These historical instances raise concerns that contact with extraterrestrials might follow a similar trajectory, with humanity potentially at a disadvantage if the extraterrestrial civilization is more advanced. Such analogies, while not definitive, suggest that the consequences of contact are unpredictable and might skew toward harm. For instance, humans often struggle with ethical considerations and empathy toward one another, let alone beings from an entirely different star system. If extraterrestrials view humanity as insignificant or merely a curiosity, they might feel no ethical obligation to ensure our well-being. Moreover, the technological gap between humanity and an extraterrestrial civilization capable of interstellar travel could be vast. Even if this civilization did not see humanity as a threat or obstacle, they might possess technology that inadvertently disrupts our systems. Advanced energy sources or communication systems could interfere with Earth's infrastructure, impacting everything from communication networks to the environment. If extraterrestrials possess highly advanced artificial intelligence or weaponry, they might not need to intentionally harm humanity, their mere presence could trigger accidental catastrophes. Humanity, in turn, might have limited means of defense. As advanced as our technology seems, it may be primitive compared to what we could encounter. For instance, if extraterrestrials use propulsion technology that manipulates spacetime, the release of such technology nearby could emit radiation or gravitational waves that harm Earth. The unknown nature of these potential technologies adds another layer of unpredictability to any encounter, leaving humanity vulnerable. Further risk lies in the intentions of extraterrestrial civilizations. If they possess goals or values vastly different from ours, even well-intentioned contact could carry unforeseen consequences. The range of motives that extraterrestrials might have is vast and unknowable. If extraterrestrial civilizations are as diverse as the species on Earth, their intentions could span from peaceful exploration to outright hostility. Some scientists, like Stephen Hawking, have warned that an advanced civilization could perceive humanity as insignificant and disposable, much like how humans view bacteria or lesser species. If extraterrestrials see Earth's resources as valuable or find humanity's presence bothersome, they might attempt to claim these resources without regard for human welfare. Alternatively, the risk might stem not from active hostility but from indifference. A civilization with vastly different values and priorities may view Earth as an insignificant speck, not intending harm but potentially engaging in activities that could inadvertently harm our planet. For instance, if their technology requires extensive energy or materials, they could deplete Earth's resources or alter our environment in ways detrimental to human life. When humans explore new environments, they often bring bacteria, viruses, and other biological agents, sometimes causing unintended ecological consequences. Similarly, if extraterrestrials were to visit Earth, they could introduce microbial life or biological agents unfamiliar to our immune systems. Even if these extraterrestrial microbes are not inherently harmful, their presence could have unforeseen impacts on our ecosystem and health. Humans might also be vulnerable to extraterrestrial pathogens or viruses operating on entirely different biological principles. These foreign microorganisms could interact unpredictably with Earth's organisms, including humans, with even minor microbial differences potentially leading to significant effects, such as the emergence of new diseases or impacts on food sources and animal populations. Beyond the physical and biological risks, contact with extraterrestrial civilizations could lead to profound psychological and societal challenges. Humanity's self-perception has long been rooted in the idea that we are unique or possibly alone in the universe. The discovery of a more advanced civilization could provoke existential crises, religious upheavals, and destabilization of long-held beliefs. The realization that superior beings may exist could profoundly impact individual and collective human identity. While some might respond with awe and inspiration, others might feel inadequate, fearful, or even hopeless. Society could fracture under these new realities, especially if the extraterrestrial civilization possesses qualities humanity cannot comprehend or match. Governments might react differently, with some seeking to harness extraterrestrial knowledge for power, while others prepare for potential conflicts. Such disparities in reaction could create global tensions as nations compete for extraterrestrials' attention or resources, if available. Fear and uncertainty could also fuel extremist movements, with some groups opposing extraterrestrial contact and others advocating for adaptation to new cosmic realities. It is also possible that extraterrestrials could bring knowledge and technology that advance human civilization in unprecedented ways, offering insights into medicine, energy, and technology that revolutionize life on Earth. However, this knowledge comes with risks. Advanced technology could be weaponized or misused by humanity, creating new dangers. For example, extraterrestrial energy or propulsion technology might lead to powerful new weapons, potentially ushering in a new era of global threats or even interplanetary conflicts. The potential misuse of extraterrestrial knowledge is not merely hypothetical. Throughout history, humans have often applied new technologies destructively, as with nuclear power being used for both energy and weapons. Similarly, contact with extraterrestrials could result in the dissemination of knowledge that, in the wrong hands, might harm humanity more than it benefits. Some theories suggest that advanced civilizations avoid contact to protect themselves or younger civilizations like humanity from potential harm. Known as the zoo hypothesis, this idea posits that extraterrestrials intentionally avoid interfering with humanity's natural development, akin to a researcher observing animals in a nature reserve. This hypothesis raises the unsettling possibility that contact with extraterrestrials might breach a protective boundary, exposing humanity to risks it is unprepared for. Alternatively, the silence from extraterrestrials could indicate that advanced civilizations understand the dangers of interaction and limit contact to avoid existential threats. Breaking this silence could open a Pandora's box of consequences we have yet to fully understand. The dark forest theory, popularized by science fiction writer Liu Cixin, suggests that civilizations avoid contact to prevent potential threats. In a vast, unknowable universe, each civilization might assume others are hostile or competitive, fearing that any signal could attract unwanted attention and lead to the annihilation of the sender. Just 4.24 light-years away, Proxima b represents one of the most promising candidates for life beyond our solar system. This exoplanet orbits within the habitable zone of its parent star, raising the tantalizing possibility that it could host conditions favorable for life. Despite this potential, many challenges complicate our understanding of this distant world. However, with the addition of the James Webb Space Telescope, a marvel of modern technology, we have achieved a groundbreaking feat, the clearest image of Proxima b to date, potentially reshaping our knowledge of our closest exoplanetary neighbor. To understand Proxima b, it's essential to begin with an overview of its discovery. Astronomers identified Proxima b using the radial velocity method, which detects the slight wobble of a star caused by the gravitational pull of an orbiting planet. This method provided strong evidence for the existence of a planet about 1.17 times the mass of Earth, orbiting Proxima Centauri every 11 days. This close proximity to its parent star places Proxima b within the habitable zone, where liquid water could exist on a planet's surface. Given that water is essential for life as we know it, Proxima b's location sparked excitement about its potential to host life. The discovery was especially significant because Proxima Centauri is the closest known star to the Sun, making its planetary system one of the most accessible for future space exploration. This proximity has opened possibilities for more detailed study and has inspired bold proposals for missions to send probes to the Proxima system in the coming decades. Despite being relatively close to us, Proxima b remains an enigmatic world. Orbiting a red dwarf star, Proxima Centauri, this exoplanet faces unique challenges. Unlike our Sun, Proxima Centauri is much smaller and cooler, and while red dwarfs are the most common stars in our galaxy, they present notable difficulties for orbiting planets. One of the intriguing aspects of Proxima b's mystery lies in its star. Known for its high activity, Proxima Centauri frequently emits powerful stellar flares, which could have a profound impact on Proxima b. These flares release radiation and charged particles that may strip a planet's atmosphere over time, potentially making it inhospitable. Proxima b orbits at only 0.05 astronomical units from its star, or about 1/20th of the Earth-Sun distance, making it particularly vulnerable to these intense stellar flares. The close proximity of Proxima b to its star raises a serious concern about the planet's habitability. Proxima b is likely tidally locked, meaning one side of the planet constantly faces the star, while the other side is in perpetual darkness. This could create extreme temperature variations between the two hemispheres. A major question scientists grapple with is whether Proxima b can sustain an atmosphere under such intense stellar conditions. If the atmosphere has been stripped away, the planet would likely be a barren, lifeless world. However, some models suggest that Proxima b might retain a thick enough atmosphere to shield its surface from harmful radiation. Alternatively, if Proxima b possesses a magnetic field similar to Earth's, it could offer protection against the star's intense radiation. Determining whether Proxima b has an atmosphere and, if so, its composition, is a critical challenge for astronomers. Positioned in the habitable zone, Proxima b might have the potential to host liquid water on its surface. However, habitability depends on more than just distance from a star. Proxima Centauri's intense stellar activity, combined with Proxima b's likely tidal locking, complicates the habitability question. In the tidally locked scenario, one side of Proxima b would remain in continuous daylight, while the other side would be in constant darkness. Between these two extremes lies the terminator line, where temperatures might be moderate enough for liquid water. This twilight zone could potentially support life if atmospheric dynamics allow heat to be distributed from the day side to the night side, creating a more temperate climate. However, if the atmosphere is thin or absent, one side of the planet could be frozen while the other is scorched. The composition of Proxima b's surface adds to the mystery. Scientists wonder whether the planet is rocky, like Earth, or dominated by oceans or ice. Spectroscopic studies with advanced telescopes like the James Webb Space Telescope could eventually reveal more about the planet's composition, but for now, it remains speculative. Some models suggest that Proxima b could harbor significant amounts of water, possibly even several times the water volume of Earth, but this is unconfirmed. Even if Proxima b has the right conditions for life, detecting signs of life from Earth is challenging. Due to its proximity to Proxima Centauri and the faintness of reflected light, direct imaging of the planet is difficult. Instead, astronomers rely on indirect methods, such as analyzing the planet's atmosphere for biosignatures, chemical markers like oxygen or methane that could suggest the presence of life. The James Webb Space Telescope plays a crucial role in these efforts. As the most powerful space observatory built to date, Webb represents a major advance in space exploration technology. With a large 6.5-meter primary mirror and sophisticated instruments, it can capture distant and faint objects with exceptional clarity. Its infrared vision allows it to penetrate cosmic dust, revealing stars, galaxies, and planets in detail. For Proxima b, the telescope's infrared capabilities are especially important. Red dwarf stars like Proxima Centauri emit most of their energy in the infrared spectrum, making Proxima b an ideal candidate for Webb's observations. Unlike previous telescopes that relied on visible light, Webb can analyze Proxima b's heat signatures, providing new insights into this mysterious world. One of Webb's primary objectives in studying Proxima b is to analyze its atmosphere. Determining whether the planet has a stable, thick atmosphere is essential to understanding its potential for habitability. Red dwarf stars, including Proxima Centauri, are known for emitting strong flares and ultraviolet radiation, which can strip away a planet's atmosphere. If Proxima b has managed to retain its atmosphere, it would be an extraordinary discovery, suggesting that planets around red dwarfs might be more resilient than previously thought. Webb uses a technique called transmission spectroscopy to study Proxima b's atmosphere. As Proxima b passes in front of its star, light filters through the planet's atmosphere, allowing scientists to examine the different wavelengths absorbed by various gases. By analyzing the spectrum, Webb can identify molecules like carbon dioxide, methane, and water vapor, which are key indicators of habitability. The infrared capabilities of Webb are particularly advantageous for this work. Earlier missions, like the Hubble Space Telescope, had limitations in detecting atmospheric compositions because they focused on visible and ultraviolet light. Webb's infrared focus allows it to detect the thermal signatures of gases, even in cooler atmospheres like Proxima Bs. The ultimate goal of studying exoplanets like Proxima b is to search for signs of life. Discovering an atmosphere alone would be significant, but detecting biosignatures, gases or compounds that suggest biological activity, would be even more profound. Webb is equipped to search for gases like oxygen, ozone, and methane, all of which could hint at life. Oxygen is a strong biosignature because it is typically produced by photosynthetic organisms, so if Webb detects oxygen in Proxima B's atmosphere, it might indicate some form of life. Methane, too, is significant. While geological processes can produce it, it is also a byproduct of biological activity on Earth. The simultaneous presence of methane and oxygen would offer compelling evidence of life. Moreover, Webb's ability to detect water vapor is crucial for evaluating Proxima B's habitability, as water is fundamental to life as we know it. In addition to atmospheric composition, understanding Proxima B's surface conditions is essential to assessing its habitability. Webb aims to provide insights into whether Proxima B's surface is Earth-like or more hostile. Key factors like surface temperature, atmospheric pressure, and the presence of liquid water all influence the potential for life. Proxima B's likely tidal locking adds to the complexity of its environment, as one side of the planet is constantly exposed to Proxima Centauri's light. This continuous exposure could make one hemisphere significantly warmer than the other, affecting the overall habitability of Proxima b. The planet Proxima b experiences extreme environmental conditions because one side of it constantly faces its star, Proxima Centauri, while the other remains in perpetual darkness. This positioning could lead to intense temperature differences between the two hemispheres. The side facing Proxima Centauri might be scorching hot, while the dark side could be frigid. However, if Proxima b possesses a thick atmosphere, it might help distribute heat more evenly across the planet, creating potentially stable conditions that could support life. The James Webb Space Telescope will measure Proxima B's heat signature using its mid-infrared instrument, known as MIRI, which is capable of detecting thermal radiation emitted by the planet. By studying Proxima B's temperature distribution, James Webb can provide insights into the composition and thickness of its atmosphere, as well as the possibility of liquid water on its surface. Understanding Proxima b is valuable not only for learning about this specific exoplanet but also for gaining knowledge about planetary systems around red dwarf stars. Red dwarfs constitute about 70% of the stars in the Milky Way, and many are known to host planets. If James Webb finds Proxima b potentially habitable, it could suggest that habitable planets around red dwarfs are more common than previously believed. Conversely, if Proxima b proves uninhabitable due to harsh conditions from its parent star, it would underscore the difficulties planets around red dwarfs face in retaining their atmospheres. Either way, Webb's observations will yield valuable data that can inform models of planetary habitability in other exoplanetary systems, helping scientists refine their understanding of the potential for life elsewhere in the universe. James Webb's exploration of Proxima b represents a new chapter in the study of exoplanets, and its advanced capabilities are poised to provide unprecedented insight into the atmosphere, surface conditions, and potential for life on Proxima b. While many questions remain, the tantalizing possibility that Proxima b could harbor life or become a second Earth for humanity has driven interest in exploring ways to reach it. However, it's essential to recognize that, while 4 light-years is relatively close compared to vast cosmic distances, it is almost unimaginably far in practical terms. For example, current human-made spacecraft, like the Voyager probes, travel at speeds around 17 kilometers per second, which would take over 70,000 years to reach Proxima b. Clearly, achieving such a journey within a human lifetime will require revolutionary advances in propulsion, energy generation, and spacecraft design, all of which remain in the early stages. One of the major barriers to interstellar travel is the absence of a feasible propulsion system. Traditional rocket propulsion, which depends on chemical reactions, is inadequate for the vast distances involved in a journey to Proxima b, so new propulsion systems are necessary. Several promising concepts have been proposed. One approach is nuclear propulsion, which could involve either fission or fusion-based technology to achieve higher speeds than chemical rockets. In a nuclear fission system, atoms of uranium or plutonium are split, releasing energy that could propel a spacecraft. Theoretically, nuclear fission propulsion could reach up to 10% of the speed of light, making the journey to Proxima b feasible in around 40 years. Fusion propulsion, which replicates the process that powers the Sun, holds even greater promise. In a fusion reaction, atoms of hydrogen fuse to form helium, releasing large amounts of energy. Although a practical fusion engine has not yet been developed, this technology promises higher efficiency and faster speeds than fission, potentially reaching 20% of the speed of light and reducing the travel time to around 20 years. Another innovative concept involves laser-powered light sails, a core idea behind the breakthrough Starshot project proposed by billionaire Yui Milner and supported by scientists like Stephen Hawking. This concept envisions small, lightweight spacecraft equipped with reflective sails that could be propelled by powerful lasers fired from Earth or space-based stations. These laser-powered sails, in theory, could accelerate spacecraft to around 20% of the speed of light, allowing them to reach Proxima b in just over 20 years. This system's primary advantage is that the spacecraft does not need to carry its own fuel, which significantly reduces its mass. However, engineering challenges are considerable, including the need for a powerful laser array to propel the spacecraft and the difficulty of steering the light sail across vast distances. A third concept, antimatter propulsion, though highly speculative, presents the most efficient means of space travel known. When matter and antimatter collide, they annihilate each other and release 100% of their energy. By comparison, nuclear fission and fusion release only a small fraction of the energy stored within atoms. An antimatter-powered spacecraft could theoretically reach speeds approaching the speed of light, allowing a journey to Proxima b in under a decade. However, producing and storing antimatter in quantities sufficient for space travel remains beyond current capabilities. The energy required to create even a minuscule amount of antimatter is astronomical, and the cost of producing just a few grams would be prohibitive. Even if a viable propulsion system were developed, significant challenges remain in sending humans on such a long journey. The voyage to Proxima b would likely span decades, even with the most advanced propulsion systems, raising several critical issues. One is human lifespan and aging. If a mission to Proxima b takes decades, human aging becomes a significant problem. One solution might involve sending multiple generations of humans on a generation ship, where the descendants of the original crew complete the journey. However, this approach raises social and ethical questions about life on a spaceship where entire generations would live and die without ever setting foot on Earth or reaching their destination. Another possibility is cryogenic suspension, which would involve freezing crew members for the journey's duration and reviving them upon arrival. Although this technology is far from mature, research in cryopreservation, especially in medicine, is ongoing. Achieving reliable and safe cryogenic sleep for humans would represent a major breakthrough for interstellar travel. Additionally, space itself poses significant risks. Beyond Earth's protective magnetic field, astronauts would be exposed to dangerous levels of cosmic radiation, which can cause cancer and other health issues. A journey to Proxima b would require advanced shielding technology to protect the crew from this radiation. Furthermore, the spacecraft would need to be entirely self-sustaining, as resupply missions would be impossible. This would mean generating its own oxygen, food, and water for the entire journey. Closed-loop life support systems, which recycle waste into usable resources, would be essential to sustaining the crew on such a prolonged mission. NASA is currently working on systems tailored for long-term missions to Mars, which could lay the groundwork for the requirements of an interstellar journey. These systems, however, would need significant scaling and refinement to support such an ambitious endeavor. Beyond technological advancements, three major psychological and social challenges arise, particularly concerning the isolation and confinement inherent to space travel. The psychological toll of a journey spanning decades could be severe, making the mental well-being of the crew a major focus. The crew would be isolated from all of humanity, with no escape from the small group they'd be living with for years. Such prolonged closeness could lead to interpersonal conflicts, which means meticulous crew selection, comprehensive psychological support, and possibly even virtual reality systems to create a more varied environment might be necessary. Alternatively, incorporating robotic or AI crew members could help lessen the psychological burden on human travelers. Considering the high risks and challenges associated with sending humans to Proxima b, some suggest that initial exploratory missions should involve robotic probes. Advances in AI and robotics could enable autonomous spacecraft to conduct scientific research, scout for habitability, and transmit data back to Earth. These robotic missions could pave the way for human exploration by gathering essential information about Proxima's atmosphere, geology, and potential for life. Moreover, they could establish preliminary infrastructure, like automated habitats or resource extraction systems, which future human crews could utilize upon arrival. In addition to these practical challenges, there are speculative concepts that might one day transform interstellar travel. Warp drives and wormholes, grounded in the theories of general relativity and quantum mechanics, offer hypothetical shortcuts through space. Although still within the realm of science fiction, they represent promising ideas. Warp drives, popularized by science fiction like Star Trek, suggest a way to achieve faster-than-light travel without violating physical laws. In 1994, theoretical physicist Miguel Alcubierre proposed a warp drive model based on Einstein's equations. The Alcubierre drive envisions creating a bubble of spacetime around a spacecraft, contracting spacetime in front of it and expanding it behind. This would allow the craft to effectively move faster than light without actually breaking the speed of light within its own spacetime bubble. The spacecraft would remain stationary within this bubble, with space itself moving around it. The practicality of the warp drive, however, faces immense challenges. One major obstacle is the energy required. Initial calculations estimated it would take energy equivalent to the mass of an entire planet to generate a warp bubble. Later studies have suggested that using exotic matter, hypothetical material with negative energy density, could potentially reduce these energy needs. Advances in understanding the mathematics and physics of warp drives are ongoing. In 2021, researchers found a new solution to the Alcubierre metric that might significantly lower the energy requirements, inching the concept closer to feasibility. However, generating and controlling a warp bubble would require manipulating spacetime itself, a feat currently beyond our technological capabilities. Furthermore, exotic matter, crucial for maintaining negative energy densities, remains theoretical and has yet to be discovered. Another exciting concept for revolutionary space travel is the idea of wormholes, also known as Einstein-Rosen bridges. These hypothetical tunnels through spacetime could connect distant points, allowing spacecraft to traverse vast distances in moments by taking a shortcut. The theory of wormholes emerges from Einstein's general relativity, and in 1935, Einstein and physicist Nathan Rosen proposed the concept of these spacetime bridges. The most familiar type in theoretical physics is the traversable wormhole, first introduced by physicist Kip Thorne in the 1980s. Unlike other solutions that collapse or form singularities, a traversable wormhole could theoretically allow safe passage from one side to the other. Creating and stabilizing a wormhole presents significant challenges. It would require exotic matter with negative energy to prevent it from collapsing before a spacecraft could pass through. Although the existence of exotic matter has yet to be confirmed, quantum field theory does allow for negative energy in small amounts, such as in the Casimir effect, which raises the possibility that future advances in quantum physics could enable the stabilization of wormholes. If wormholes could be created and stabilized, they might facilitate instantaneous travel between distant points in space. For instance, a wormhole linking our solar system to another galaxy could drastically reduce travel time across otherwise unreachable distances. Wormholes also raise intriguing possibilities for time travel, as they connect points in spacetime, theoretically allowing movement through both time and space. However, time travel through wormholes remains speculative and is complicated by potential paradoxes. In summary, traveling to Proxima b presents formidable challenges but may not be beyond the realm of possibility. With advancements in propulsion technology, human biology, and spacecraft design, the dream of interstellar travel could become a reality within the next few centuries. Although the technical and logistical obstacles are daunting, the desire to explore and expand beyond our solar system is a powerful motivator. As we stand on the threshold of becoming an interstellar species, Proxima b serves as both a destination and a symbol of humanity's enduring quest for knowledge and exploration. One day, perhaps, we will look back on this time as the moment we first began our journey to the stars. What's notable is that, besides Proxima b, there are other potential homes beyond Earth. Here is a quick look at some of the most promising exoplanets that scientists believe could harbor life or offer clues to the formation of planetary systems. The TRAPPIST-1 system, located 39 light-years away in the constellation Aquarius, has become a focal point in the search for habitable worlds. It consists of 7 rocky planets, 3 of which, TRAPPIST-1e, TRAPPIST-1f, and TRAPPIST-1g, are located in the star's habitable zone. What makes this system especially remarkable is that all 7 planets are roughly the size of Earth and are so close to one another that an observer on one planet could likely see the others in the sky. The TRAPPIST-1 star is a red dwarf, much cooler and dimmer than our Sun, allowing the planets to orbit much closer to the star without experiencing extreme heat. This compact arrangement also simplifies the study of the system, as scientists can observe how the planets interact gravitationally, gaining insights into their masses and compositions. TRAPPIST-1e, in particular, stands out as a candidate for habitability. Its location in the middle of the habitable zone suggests it might have liquid water on its surface, and its density points to a rocky composition similar to Earth's. While the system's planets likely experience tidal locking, there is potential for atmospheric circulation to distribute heat, making parts of the planets temperate and possibly habitable. Elsewhere, LHS 1140b is another top candidate. Discovered in 2017, LHS 1140b is a super-Earth orbiting a red dwarf star about 49 light-years from Earth. This rocky planet is about 1.4 times the size of Earth but has 6 times Earth's mass, indicating it is exceptionally dense. LHS 1140b orbits its star at just the right distance to lie within the habitable zone, making it a promising candidate for habitability. What sets LHS 1140b apart is its atmosphere. Scientists have detected a potentially thick atmosphere that may shield the planet from harmful radiation and help maintain surface temperatures conducive to liquid water. Given its mass and size, the planet's gravity could help it retain this atmosphere even under the radiation bombardment from its star. Its relatively close distance to Earth and the presence of a dense atmosphere make it a target for further exploration, particularly with instruments like the James Webb Space Telescope, which can analyze its atmospheric composition in detail. If it harbors signs of water vapor or even biosignatures like oxygen, it could become one of the most significant discoveries in exoplanet science. Kepler-452b, discovered by NASA's Kepler mission, has been dubbed Earth's cousin due to its size and location in the habitable zone of a Sun-like star. Located 1,400 light-years away, Kepler-452b is about 60% larger than Earth and orbits a G-type star similar to our Sun, although it is slightly older. The estimated age of Kepler-452b's star, around 6 billion years, raises fascinating questions about the planet's evolutionary path. If Kepler-452b had conditions conducive to life in its past, it may have supported life for billions of years, potentially giving it a significant evolutionary head start compared to Earth. However, its older star means it may now be experiencing a runaway greenhouse effect, where rising temperatures lead to water evaporation and the loss of habitable conditions. Although Kepler-452b's distance from Earth makes it challenging to study in detail, its Earth-like qualities and its orbit around a Sun-like star make it a crucial reference point in understanding planetary habitability. Future telescopes might reveal more about this distant exoplanet. K2-18b is a fascinating super-Earth located 24 light-years away in the constellation Leo. What makes K2-18b extraordinary is the detection of water vapor in its atmosphere, making it the first exoplanet in the habitable zone with confirmed water vapor. This discovery, made by the Hubble Space Telescope in 2019, immediately positioned K2-18b as one of the most promising candidates for further study. K2-18b is about 2.6 times Earth's size and 8.6 times its mass, making it likely a mini-Neptune with a thick atmosphere of hydrogen and helium. Despite its gaseous nature, it may have a rocky core and liquid water, a combination that intrigues scientists searching for signs of life. The presence of water vapor raises the possibility that liquid water could exist on the planet's surface or within its atmosphere. Proxima c, another planet in the Proxima Centauri system, has also drawn the attention of astronomers since its discovery in 2020. Unlike Proxima b, Proxima c orbits much farther from its parent star, making it an unlikely candidate for life as we know it. However, its large size, estimated at about 6 times that of Earth, makes it a compelling object for study. Proxima c may have a thick atmosphere or even rings similar to those of Saturn. While it lies outside the habitable zone, studying this planet could provide valuable information about planetary formation and the dynamics of multiplanet systems. Additionally, Proxima C's proximity to Earth makes it an excellent candidate for future direct imaging missions. That's all the information we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. Let us know what you think about today's content. Your support motivates us to continue delivering quality content and always improve. As always, thanks for watching, and we'll see you next time.